quantum numbers, lecture number 2. So in the last lecture we talked about introduction to light and how light can interact with electrons in the atom to cause them to either raise or lower in energy. Right? So that we can have light come into an atom and take an electron and raise it to a higher energy level, or we can take an electron and go from a higher energy level down to a lower energy level, giving off light. One of the interesting things we didn't mention in the last lecture is that because of this and some other properties, light can be thought of as both a particle and a wave. Right? So it can interact in both those. We can describe some of its properties as a particle and some of the other properties as a wave. A lot of what we talked about last time was those wave properties. We sort of ignore the particle properties, but we can actually get light to hit things and move electrons like we would a normal object, which makes it like a particle. We can see then that if we can treat these electrons much the same way. So Schrödinger in 1926 wrote an equation that describes both the wave-like properties of an electron with the particle-like properties. Right? So we can now describe the movement or the position of an electron based on the fact that it's both a particle and a wave. Right? And he described this equation as the wave function, which I have listed here as a y, but it's really a psi. The energy, and in this wave function, if we solve this wave function, we can get the energy of an electron for each given wave function. So a single electron will have a single wave function. And if we solve these Schrödinger's, or these wave functions, we can get the probability of finding an electron in some given volume of space. So notice we can do either one or the other. We can't describe both the position of an electron and its speed or its energy and its position. So because of this sort of problem, we typically will talk about finding electrons in probabilities, a certain volume, at a certain energy, not necessarily as fixed position. Right? Schrödinger equation, as it sounds, is fairly complex, so it has only been solved exactly for the hydrogen atom. For all other ones, we're making some approximations to get these solutions. So we'll see some direct results of the hydrogen atom, the single electron species, but when we start putting additional electrons in there, we have what we call a two-bonding problem, and makes solutions become very non-trivial, is the math word they use. So, but we're not actually going to solve these wave functions in this course. That takes some calculus. What we're going to do is see the results. What we're going to do is define these probabilities of where we're going to find electrons in an atom. Right? So to do that, we sort of set up this for what we call quantum numbers, to sort of pinpoint where around this nucleus we would expect to find a certain electron. Right? So the first one of these quantum numbers is the principal quantum number n. Right? We abbreviated it. We've seen examples of n earlier when we talked about the Reinberg equation of the hydrogen atom. Those different energy levels were defined by this principal quantum number. N can be any positive integer, 1 to infinity. We'll see that the likelihood of n being a certain value in chemistry is more likely than others, but it can be theoretical any value from 1 to infinity. And what it describes is, in general, the distance away from the nucleus that these electrons are located. So n equal 1, which is going to be much closer than n equal 4. It doesn't say anything else except for the general distance away from this nucleus. So if you look down here, you can see as we go from 1 to 3, we get that sphere gets larger and larger, indicating that distance from the electron or the nucleus is getting bigger. So that's our first quantum number. The principal quantum number tells us the distance. The next quantum number we describe as the angular momentum quantum number, which we abbreviate as L. The values of L depend on n. So if we have a given value of n, then L can be anywhere from 0 to n minus 1. So if n is 1, as you can see, L must be 0. if n is 2, then L can be either 0 or 1. N is 3 follows that L can either be 0, 1, or 2. All of those different possibilities exist depending on the value of n. Right? And this angular momentum quantum number really defines for us the volume of space that occupies. Right? So it sort of tells us what sort of shape this orbital or this sort of volume is going to occur. Right? And because of that, we've defined a shorthand notation for when L is equal to 1. You can see here, then we call that an s orbital. It has a certain shape. When L is equal to 1, L is equal to 0, we call that an s orbital. When L is equal to 1, we call that a p orbital. When L is equal to 2, a d orbital. L is equal to 3, an f orbital. 4 would be a g orbital, and then from there it goes alphabetically. We're mostly going to talk about this s, p, d, and f here. Right? So n, the principal quantum number, tells us the distance from the nucleus. This L, the angular momentum quantum number, tells us the shape of this orbital. To give you an idea of what those look like, you can see here on this slide we have the s, the p, and the d orbitals listed. So s we typically talk about being as a sphere. P is commonly referred to as the dumbbell notation, and then d's, there's a variety of different d possibilities down here at the bottom when L is equal to 2. I want you to be familiar with these shapes, especially the S and the P. We'll talk a little bit about the D's, but we're not going to focus on those shapes because you can see some of them are sort of different. So the third quantum number out of the 4 is the magnetic quantum number, m sub L. Right? Like L, m sub L is going to depend on the previous quantum number, in this case L. So ml is going to be anywhere from a negative L through 0 to a plus L. Right? And this is going to define how that shape is oriented in space. We'll sort of get to the notate what that means in a minute. So if we go back, if n is equal to 1, L has to be equal to 0, which means m sub L has to be equal to 0. If n is equal to 2, then L will be 1, and if L is 1, then ML can either be a negative 1, 0, or a plus 1. Again, for that one value of L, there's 3 possibilities. For when L is equal to 2, now ML can either be a negative 2, negative 1, 0, 1, or 2. So now we have multiple possibilities. So as we go further away from the nucleus, the principal quantum number increases. The possibility of different orientations is going to increase. So if we think about when n is equal to 0 or 1, L is equal to 0, m sub L has to be equal to 0. There's only that one shape, that sphere that we've seen. When we have the p orbitals or the d orbitals when L is equal to 1 or 2, now we have multiple different possibilities for L, which gives us these multiple possible values for m sub L. Right? And this is an approximation. They're not necessarily saying that m sub L minus 1 is this orientation, but it's an approximation. So right, you see I have 3 possibilities when L is equal to 1 for m sub L gives us the 3 different orientations along the 3 different axes for this possibility. In the D, now there's 5 different possibilities for m sub L, and you see that there are 5 different possible arrangements for those d orbitals. Okay. So to review, so what we're talking about here is that we're really defining a probability. So if we look at an s orbital, as here, the density, the probability density sort of is, there's a certain point where our probabilities are the largest, and that's sort of what's defining this space. Right? So an s orbital here, we can say 90% of the electron density or probability of finding an electron in this s orbital is going to be this distance, spherical distance, which gives us that spherical orbital. Right? So if we look at the p orbitals, there are some probabilities where we have a higher, and that's not equally shared around the nucleus. So let's review these three quantum numbers again. We have the principal quantum number n, can be any positive integer from 1 to infinity, gives us the distance from the nucleus. The angular momentum quantum number L depends on n, and it's going to go from 0 to n minus 1. Tells us the shape of these orbitals. When it's 0, that is going to be an S. When it's a 1, it's a P. When it's a 2, it's a D. When it's a 3, it's an F. The angular momentum quantum number, m sub L, again depends on L, and it goes from a negative L through 0 to a plus L, and it tells us how that shape is oriented in space. So the more possibility arrangements, the more possible values for m sub L, the more possible arrangements. So that's 3. I said there was 4. The fourth quantum number is what we call the spin quantum number, and we can think about it as being not necessarily the electron spinning, although that is sort of one context in one direction or the other, but it's sort of like the poles on a magnet, whether we have a positive, negative, and how that is oriented. We see through this bottom figure here, if we pass electrons through this magnetic field, we see that some of the electrons are going to be pulled up, some of them are going to be pulled down, which gives us an indication that there is some additional factor. Not all electrons are the same. And the values for this spin quantum number, m sub s, is either a plus 1/2 or a minus 1/2. Right? So for every possible value of m sub L, there's 2 possible values for ms, a plus 1/2 or a minus 1/2. Right? So we're going to talk about what these assigning the possible quantum numbers here, but then we'll talk about what that means for different electrons as we move into the next phase.
Dad, I done did it.